Okay, so continuing on with our discussion of the frequency response, we'll pick up sort of where we left off last time, which is looking at the frequency response or the Bode plots for a first order low pass filter like this, omega naught over S plus omega naught. This is actually a very typical first order transfer function form. And it's important to know that any transfer function that has this form is going to have a very similar Bode plot. The only difference is that the cutoff frequency, this omega naught, may change from transfer function to transfer function. Okay, so some of the key elements that we picked up last time were that, well, up until that cutoff frequency omega naught, the Bode magnitude is essentially equal to 1. For frequencies larger than omega naught, the Bode magnitude starts to attenuate. In other words, it starts to decrease or get smaller, and it does so at a rate of -1 decade per decade on the log-log Bode magnitude plot. This is typical for first order systems, this slope of -1. What we also what we also discovered was that the phase plot it starts at 0 degrees phase for very low frequencies, passes through -45 degrees at the cutoff frequency, and continues on and approaches -90 degrees for all frequencies, for all larger frequencies. Okay, this is a very typical first order transfer function Bode plot. And the point of today's lecture is to sort of zoom out a little bit and give you sort of a library of fundamental transfer functions so that given any transfer function, higher order, third order, fourth order, and so forth, you can sort of pick out what the Bode plots will look like based on your understanding of these fundamental transfer functions. Okay, so we're gonna ultimately cover 7 fundamental transfer functions today, and in the next lecture, we're going to learn how we can use the general shapes of those 7 fundamental transfer functions to sketch the Bode plot for any arbitrary order transfer function. Okay, so a little bit of a setup lecture today, just to introduce these 7 fundamental transfer functions. But hopefully the payoff will be worth it in the next lecture. Okay, so omega naught over S plus omega, that always has this shape of a Bode plot. Um, the only difference is really this cutoff frequency omega naught. If we were to flip that, for example, S plus omega naught in the numerator and omega naught in the denominator, the Bode plot looks like this. It's actually perhaps what you might expect. It gets flipped. So still the magnitude starts at 1, but actually for frequencies higher than omega naught, you end up getting this exponential you end up getting this magnification in the output. So it's not attenuation, but rather amplification, where the output becomes larger than that of the input. And this happens at a rate of 1 decade per decade in the log-log plot. The phase, the phase starts at 0, and rather than decreasing and starting to lag, it actually starts to lead the input. Okay, so it means we pass through positive 45 at omega naught, ultimately settling at positive 90 degrees of phase lead in the system. And this is very typical for this type of transfer function where you have the first order polynomial in the numerator. Okay, so this is your second fundamental transfer function, and this basically covers all of your first order transfer function scenarios. You either have a pole in the numerator or a pole in the denominator, right? Okay, so if we move on to second order systems, things get a little bit more involved here. It's not quite as simple as just moving that cutoff frequency, but we can see what second order transfer function Bode plots will look like. Okay, so this is just back to our general second order transfer function. And basically, without going through the entire derivation, we can do something similar to our analysis in lecture 19. So if you go back to if you go back to lecture 19, you can see that we basically, we wrote P of j omega as a real part plus an imaginary part, and then from there we were able to derive the magnitude and phase functions using these terms. So the magnitude would be using Pythagorean theorem, real squared plus imaginary squared, and this would be, the phase would be the arctangent of the imaginary part over the real part, right? So this is how we actually got the analytical magnitude and phase functions. From there, we could just plot magnitude and phase for various frequencies to actually produce the Bode plots. Okay, so that's what we did in lecture 19. We could do something practically identical for second order systems, and what you would end up with is a typical second order Bode plot that looks like this. Okay, so this is your typical second order Bode plot. So if you have second order denominator, this is generally what you're going to see. To note, at least for the phase, you start at 0 and you're always going to end up at minus 180 degrees at a phase. You pass through negative 90 at the cutoff frequency, which, by the way, in the numerator, the cutoff frequency is defined as omega not squared. So it's actually the value being squared that's the cutoff frequency. Okay. The other thing is that in the Bode magnitude, you're going to see a steeper rate of decay. So you're going to see for every 1 decade on frequency, you're going to attenuate by 2 decades on the magnitude spectrum. Okay, so the slope is steeper for second order, and it's no coincidence that first order is a slope of -1, second order is slope of -2. That carries for higher orders as well. The thing that you may notice here is that there's this hump, right? This is called a resonant peak, and this is unique for second order systems. First order systems don't have resonant peaks due to the nature of their dynamics, but second order systems may or may not have a resonant peak. Okay, so a second order system could either look, in the magnitude anyways, could either look like what I've drawn here, this orange plot, or if it doesn't have a resonant peak, it will simply transition to that slope of -2, like so, without a resonant peak. Okay, and what you need to be aware of for second order systems is how to check to determine if a resonant peak exists. Okay, so the formula for resonant peak I'll give you here. But the idea is for resonance, you always need to check for a particular second order system if resonance is going to occur. Okay, so omega r is defined as the square root of 1 minus 2 zeta squared times omega naught. Okay, so whatever zeta is, you can compute the resonant frequency as a function of zeta and the undamped natural frequency, omega naught. You can also, there's also a formula to compute the max amplitude. Right? So what is the actual amplitude at that frequency? That's equal to the following. So it's 1 over 2 zeta square root 1 minus zeta squared. Okay, so these are two things that you'll have to check for, and it turns out, right? It turns out that resonance only exists for. I'll write it here. Resonant peak exists for zeta is less than root 2 over 2. And I'll explain this in a little bit. I'll do a little computation in a second about this. But the point here is that for second order systems, you actually have to check to see if resonance will exist by computing zeta first. Okay, so you need to know what zeta is. If it's less than root 2 over 2, you will see a peak here. If it's greater than root 2 over 2, you will not see a peak. You'll just see something like this green plot where you have a smooth roll-off. Okay. The resonant frequency is always going to be equal or less than the undamped natural frequency if you just look at this computation here. So it'll be somewhere perhaps here, omega r, the resonant frequency. So this peak here doesn't exactly line up with the undamped natural frequency. Now you can see as zeta approaches 0, right, this parameter here, zeta, if the damping ratio approaches 0, then by definition you're approaching the undamped case, in which case the resonant frequency will align exactly with the undamped natural frequency. And that's only in the extreme case that zeta equals 0. Okay, so this is your typical second order system. But there are two versions of this, just like there were with first order. Right? So another version of a second order transfer function is, again, the inverse of that. And in this case, just as you would expect, you would see basically the inverse of what we saw for the previous second order system. You would see basically 1 up until you approach the undamped natural frequency, omega naught, and then you may see what's called an anti-resonant peak where it dips before increasing and magnifying at a rate of 2 decades per decade. So this is referred to as an anti-resonant peak. Okay, and that would occur at the resonant frequency. And then on the phase, you'd start at 0. You'd end up at 180, passing through 90 degrees at the cutoff frequency, like so. So this is your typical Bode plot for a transfer function of this nature. Okay. Now the check again, the check here is to see if there's an anti-resonant peak or not. Right. In this case, for this transfer function, you'll either see something like this Bode magnitude plot in orange, or something like this Bode plot in green. Right. And again, you've got to check to see if there's resonance in the system. Okay, so again, the formula is the same for whether there's resonance or anti-resonance. Omega r is equal to square root 1 minus 2 zeta squared omega naught. Did I put the squared above? I did. Okay. So this is a formula for resonant frequency or anti-resonant, right? It just depends on the nature of the transfer function. So if the second order polynomial is in the numerator, you're basically checking to see if there's an anti-resonant peak or not. If the second order polynomial is in the denominator, you're checking to see if there is a resonant peak or not. And the criteria is the same for both scenarios. You're checking to see if zeta is less than root 2 over 2. Okay. If we look at this very quickly, this argument here, square root of 1 minus 2 zeta squared. In order for this to be a real value, then the argument inside of the square root sign has to be positive, right? So 1 minus 2 zeta squared, that has to be 0. Otherwise, you're going to get an imaginary number, and that's strange. There are no imaginary frequencies. Okay, so this condition has to be true, and what this does is it places criteria on zeta. So this is where that root 2 over 2 comes from. This would say that zeta has to be less than root 2 over 2. And of course, zeta can't be negative. So the criteria actually comes from here, that root 2 over 2. It's basically that the argument inside of this square root sign has to be positive in order for you to have a real valued resonant peak. Okay, so the check for resonance or anti-resonance is zeta less than root 2 over 2. And to determine if you're checking for resonance or anti-resonance, you look at the nature of the transfer function, right? So in this transfer function here, all you're doing is seeing if there's a resonant peak or not. I'm sorry, an anti-resonant peak or not. in this transfer function up here, you're only checking to see if there's a resonant peak or not. Okay, so we can kind of see what's going on. We can kind of see what's going on with second order systems by running a very simple MATLAB script. Okay, so all I'm doing here is defining that generic second order transfer function. I've got omega and zeta as variables so I can mess around with them. And I'm just looking at the Bode plots as I adjust zeta, which is the damping ratio. Okay, so the Bode plot for when zeta equals 1 looks very much like a first order transfer function. You can see you got that sort of roll off and it starts to attenuate. Only, as we've expressed before, the slope, right? You'll notice that for every decade on the log scale, so 10 to the 0 to 10 to the 1, we're actually decreasing by 2 decades on the magnitude scale. So the slope is steeper. And for the phase, we got 0 to negative 180 passing through negative 90 at the cutoff frequency, which is 1 in this case. What's interesting here is if I start to reduce zeta, start to dial zeta back to say, zero point 0.8, then you see something interesting. So if zeta equals 0.8, you still don't see any resonant peak. The critical point is zeta equals square root of 2 over 2, as we found. But when zeta is equal to root 2 over 2, you actually still don't see any resonance. Okay, so this yellow line pops up here. Anything less than root 2 over 2, however, like 0.4 or 0.5, you will start to see a hump, right? So there's some magnification that happens in the output, which just means that the magnitude gets larger than 1. And we can keep adding to this for smaller and smaller values of zeta. What you're seeing, hopefully, what you're observing is that the smaller the value of zeta, the larger the resonant peak is going to be. Okay, and so for very, very small values of zeta, it can be a bit concerning because if you were to excite the system at that resonant frequency, right at that peak, you can see that the value is very large, right? It's 36.5 times larger than the input value. Okay, so this is one reason why the Tacoma Narrows Bridge video is such a prominent example of resonance, is because you can really see how the input sine wave has really been amplified in the output, and that's what caused the destruction of that bridge. Okay, so all I'm doing here is showing you the Bode plots for different values of zeta. What you notice is you don't see a peak until zeta is less than root 2 over 2. Furthermore, the height of that peak increases as zeta shrinks and tends towards 0. On the phase, interestingly, the steepness or the transition of the phase from 0 to negative 180 happens much more quickly as you decrease zeta. Okay, so that's just another sort of property of second order systems as it pertains to zeta. So this is sort of a visualization of what's going on with the Bode plot as zeta approaches 0. Now, in addition to essentially the 4 transfer functions that we've seen so far, there are a few special transfer functions that we should consider as well. There's 3 of these, and they don't fall into your typical first order, second order category. Okay, the first one that we're going to take a look at is the case where you have one pole at the origin. This one's interesting because it highlights a couple of unique features. So we can pretty quickly take this through the whole analysis where we compute the frequency response function, which is just 1 over j omega. If we were to conjugate this so that we can write it as real plus imaginary, we find that pretty quickly we can discover that the frequency response function can be written as the following. It's essentially minus j omega over omega squared, because if we conjugate the denominator, we should end up with the real valued denominator. But I prefer to write this as 0 minus 1 over omega j. And I wrote it this way because now we have it in terms of the real component in the imaginary component, which means we can actually compute the magnitude function, which is given as square root of real squared plus imaginary squared. And in this case, the magnitude function just works out to be 1 over omega. So it's sort of like this is inversely proportional to the frequency that you input. For the phase, we just plug into our formula, arctangent of the imaginary part over the real part, which is 0, which gives us negative 90 degrees. Okay, so for all frequencies, the phase is going to be a constant value. What this looks like on the Bode plots is the following. Okay, so we're going to have, at least on the phase, this is pretty straightforward. We're just going to have a constant phase of negative 90 degrees. The Bode magnitude, this is interesting because it's just an inverse relationship to the magnitude. Okay, so we're just going to get simply sort of this sloping line that goes like this with a slope of minus 1 decade per decade. What I want to highlight here is that I'm specifically not allowing this arrow to intersect with the imaginary axis, right? I'm just drawing an arrow that indicates that log-log plots have no origin, right? And you can see that in the equation itself. 1 over omega is the expression for the magnitude. So as omega approaches 0, the Bode magnitude actually approaches infinity. It will never actually intersect with the vertical axis because on a log-log scale there is no origin. So the way to express that is just to sort of draw an arrow that points up to the left for all small frequencies that approach 0. So it's a very interesting Bode plot here. You might guess that the next sort of special transfer function is simply the inverse of the one that we previously did. And you could do a similar thing with computing the frequency response function, getting the magnitude and phase functions, but you'll find very quickly that the Bode plot is, again, for this transfer function, it's just the inverse of up here. You've got a positive slope of 1, and you have a constant phase of positive 90 for this transfer function, just equal to s. And then the last special transfer function we'll look at is just a constant value, right? So just a constant value, and this one isn't too tricky at all because the frequency response function you get again by plugging in j omega everywhere you see s. Well, there is no s in this transfer function, so the frequency response function is simply a plus 0j, which gives us that the Bode magnitude is just a constant value, and the Bode phase is just 0 degrees. So this is a very simple transfer function, but it's a critical one to understand because many times when you're factoring out more complicated transfer functions to try and sketch the Bode plot, you end up with a constant floating out in front, and you have to account for that somehow. Okay, so the Bode plot for a constant value is basically it contributes a constant a constant value for the magnitude across all the frequencies, and it contributes 0 phase to the overall system. So this is a Bode plot for a constant valued transfer function. Okay, so what we've done today very briefly is to sort of outline these 7 fundamental transfer functions. And what I have here is a summary of all of those transfer functions in one nice location. Okay, so the 7 fundamental transfer functions, according to Professor Tsuchiya, is this set here, where you've got the 2 first-order transfer functions that are basically inverses of each other. And in here, for these ones, you have no chance for resonance or anti-resonance, so these are basically it. The only thing that changes is, of course, the cutoff frequency. For second-order systems, you either have the case where you have a resonant peak or potentially an anti-resonant peak. but you don't know until you check to see whether or not there is resonance or anti-resonance. Okay, so you have to check by computing zeta to see if it's less than root 2 over 2, and these will be your corresponding Bode plots. And then, of course, there's these three sort of special transfer functions, and the way that a program like MATLAB would indicate Bode plot for, say, P5 is it actually does intersect that line with the vertical axis, which I somewhat disagree with, because this is a log-log scale. And so the fact that the vertical axis on this set of axes intersects with 10 to the minus 1 is a bit of a misnomer, right? Log-log scale has no origin. We just approach 0 and infinity sort of exponentially. So I prefer to leave a little gap here just so that you know that it really never intersects with the vertical axis. And the same is said about P6, where it's just the inverse of P5. You have a positive 1 slope here. And then the last transfer function is just a constant value. So you just get a constant at whatever value A is, and you get no contribution to the phase whatsoever. And there's even a note here that indicates for P5 and P6 that you should never really assume that these lines will intersect with the vertical axis. Okay, so the point of this lecture was to sort of expand your scope a little bit and understand that there are different Bode plots for different transfer functions, obviously. But what I'm sort of setting you up for now is, if you understand what the Bode plots for these 7 fundamental transfer functions look like, then it turns out through a little bit of analysis we can very easily sketch the Bode plot for any arbitrary order transfer function that I give you. And that's going to be the topic for the next lecture. So we'll see how to combine all of these and essentially do graphical superposition of several simpler transfer functions to make up the Bode plot for a much more complex system.